Welcome to the world of VLSI design. VLSI stands for Very Large Scale Integration, a technology that has revolutionized the electronics industry. It refers to the process of integrating millions or even billions of transistors onto a single chip. This advancement has made modern electronic devices smaller, faster, and more efficient. In this video, we'll explore the fundamentals of VLSI, its significance, and how it shapes the technology we use every day. Let's embark on this journey to understand the backbone of modern electronics. Story of VLSI begins in the 1970s, when engineers sought ways to pack more functionality into smaller chips. Early integrated circuits contained only a few thousand transistors. With the advent of VLSI, this number skyrocketed, enabling the creation of complex microprocessors and memory chips. This leap in integration paved the way for personal computers, smartphones, and countless digital devices. Understanding the history of VLSI helps us appreciate how far technology has come and sets the stage for future innovations. Integrated circuits, or ICs, are the building blocks of VLSI design. An IC is a set of electronic circuits on a small flat piece of semiconductor material, usually silicon. These circuits can perform various functions from simple logic operations to complex computations. The ability to integrate multiple components onto a single chip has made electronics more reliable and cost-effective. In VLSI, the scale of integration is so high that entire systems can fit onto a single chip, leading to the term system-on-chip. Transistors are fundamental to VLSI design. They act as electronic switches, controlling the flow of current in a circuit. In VLSI chips, millions or even billions of transistors are packed together to perform complex operations. The miniaturization of transistors has allowed for greater processing power and efficiency. As technology advances, transistors continue to shrink, enabling even more powerful and compact devices. Understanding transistors is key to grasping how VLSI chips function. Moore's law predicts that the number of transistors on a chip doubles approximately every 2 years. This observation has guided the semiconductor industry for decades, driving rapid advancements in VLSI design. As chips become more densely packed, their performance increases while costs decrease. However, as we approach physical limits, new challenges arise in maintaining this pace. Moore's law remains a central concept in understanding the evolution and future of VLSI technology. VLSI design process follows a structured flow, starting from system specification and ending with chip fabrication. Key steps include design entry, logic synthesis, verification, physical design, and testing. Each stage is crucial to ensure the final chip meets performance, power, and area requirements. This systematic approach helps designers manage the complexity of modern integrated circuits and deliver reliable products. Let's take a closer look at each stage in the VLSI design flow. First step in VLSI design is system specification. Here, designers define what the chip is supposed to do, including its functions, performance targets, and constraints. This stage involves close collaboration between engineers, product managers, and customers to ensure all requirements are captured. A clear and detailed specification serves as the blueprint for the entire design process, guiding decisions and trade-offs in later stages. Design entry is where the actual design begins. Engineers use hardware description languages like VHDL or Verilog to describe the chip's behavior and structure. This step translates the system specification into a formal representation that can be processed by design tools. Accurate design entry is essential, as errors here can propagate through later stages. Modern tools provide simulation and visualization features to help designers catch issues early. Logic synthesis converts the high-level design into a gate-level representation. This process maps the design onto standard logic gates, optimizing for speed, area, and power. Synthesis tools automatically generate the netlist, which describes how the gates are connected. The goal is to create an efficient and functional circuit that meets the original specifications. Logic synthesis bridges the gap between abstract design and physical implementation. Verification ensures that the design works as intended. This stage involves extensive simulation and testing to catch logical errors and design flaws. Verification can be performed at different abstraction levels, from functional simulation to formal verification. Catching errors early saves time and resources, preventing costly mistakes in later stages. Verification is a critical step in delivering reliable VLSI chips. Physical design translates the logical representation into a physical layout. This involves placing and routing the components on the silicon chip, ensuring that all connections are made correctly. Designers must consider factors like timing, power consumption, and signal integrity. The physical design stage is crucial for achieving optimal chip performance and manufacturability. Advanced tools help automate much of this complex process. Design for testability (DFT) is an important aspect of VLSI design. It involves adding features that make it easier to test the chip after fabrication. Techniques like scan chains and built-in self-test help detect manufacturing defects and ensure product quality. DFT is integrated throughout the design process, balancing testability with performance and area constraints. Effective DFT strategies reduce testing costs and improve yield. Once the design is finalized, the chip moves to fabrication. This process involves creating the physical chip on a silicon wafer using photolithography and other advanced techniques. Fabrication is a highly complex and precise operation, requiring cleanroom environments and specialized equipment. The result is a wafer containing many identical chips, which are then cut, packaged, and tested. Fabrication is where the design becomes a tangible product. After fabrication, chips are packaged to protect them and provide connections to the outside world. Packaging involves enclosing the chip in a protective case and attaching pins or balls for electrical connections. The packaged chips undergo rigorous testing to ensure they meet specifications and are free from defects. Only chips that pass these tests move on to be used in electronic products. Packaging and testing are vital for product reliability. Modern VLSI design relies heavily on specialized software tools. These tools assist with design entry, simulation, synthesis, layout, and verification. Popular tools include Cadence, Synopsys, and Mentor graphics. Automation provided by these tools allows designers to handle the complexity of today's chips, speeding up development and reducing errors. Mastery of design tools is essential for any VLSI engineer. VLSI design can be broadly categorized into analog and digital domains. Digital VLSI deals with binary signals and logic circuits, forming the basis of processors and memory. Analog VLSI handles continuous signals, used in amplifiers, sensors, and communication circuits. Many modern chips combine both, known as mixed-signal VLSI. Understanding the differences helps designers choose the right approach for each application. System-on-Chip, or SoC, is a major achievement of VLSI technology. And SoC integrates all components of a computer or electronic system onto a single chip, including processor, memory, input-output, and more. This integration reduces size, power consumption, and cost, making SoCs ideal for smartphones, tablets, and embedded systems. SoC design is a complex process, requiring expertise in multiple domains. VLSI design often involves two main types of chips, ASICs and FPGAs. ASICs, or application-specific integrated circuits, are custom designed for a particular application, offering high performance and efficiency. FPGAs, or field programmable gate arrays, are reconfigurable chips that can be programmed after manufacturing. Each has its advantages and trade-offs, and the choice depends on the application's requirement. Power consumption is a critical concern in VLSI design, especially for portable devices. Low-power design techniques include clock gating, power gating, and voltage scaling. These methods help reduce energy usage without sacrificing performance. Designers must carefully balance power, performance, and area to meet the demands of modern applications. Low-power design is essential for extending battery life and reducing heat. Physical constraints play a major role in VLSI design. Designers must consider chip area, power dissipation, timing, and signal integrity. These constraints influence every stage of the design process, from architecture to layout. Managing physical constraints is key to achieving a successful and manufacturable chip. Advanced simulation and analysis tools help designers optimize their designs within these limits. Timing analysis ensures that signals within the chip arrive at the right place at the right time. This process checks for timing violations that could cause errors or reduce performance. Static timing analysis is commonly used to evaluate all possible paths in the circuit. Accurate timing analysis is crucial for high-speed designs, ensuring reliable operation under all conditions. Signal integrity refers to the quality of electrical signals as they travel through the chip. Issues like crosstalk, noise, and reflections can degrade signal quality, leading to errors. Designers use various techniques to maintain signal integrity, such as shielding, proper routing, and careful layout. Ensuring signal integrity is vital for the performance and reliability of VLSI chips, especially at high speeds. Clock distribution is a critical aspect of VLSI design. The clock signal synchronizes operations across the chip, ensuring all parts work together. Distributing the clock evenly is challenging, especially as chips grow larger and faster. Designers use techniques like clock trees and meshes to minimize skew and delay. Effective clock distribution is essential for high-performance VLSI systems. Power distribution ensures that all parts of the chip receive adequate power. As chips become more complex, delivering stable power becomes more challenging. Designers use power grids, decoupling capacitors, and careful layout to manage voltage drops and noise. Proper power distribution is crucial for reliable operation and preventing failures due to power issues. Floor planning is the process of arranging functional blocks on the chip. Good floor planning minimizes wire lengths, reduces delays, and improves performance. Designers must balance area, power, and timing constraints while placing components. Effective floor planning is a key step in achieving an optimal physical design and manufacturable chip. Placement and routing are crucial steps in physical design. Placement determines the exact location of each component, while routing connects them with metal wires. The goal is to meet timing, area, and power constraints while avoiding congestion and crosstalk. Automated tools help designers handle the complexity of modern chips, ensuring efficient and reliable layouts. Design rule checking (DRC) verifies that the physical layout complies with manufacturing rules. DRC tools check for violations like minimum spacing, width, and overlap. Ensuring compliance prevents fabrication issues and increases yield. DRC is an essential step before sending the design to fabrication, safeguarding against costly errors. Layout versus schematic (LVS) is a verification step that compares the physical layout to the original schematic. LVS ensures that the layout accurately implements the intended circuit. Any discrepancies are flagged for correction. LVS is critical for catching errors that could lead to non-functional chips, ensuring design integrity before fabrication. Parasitic extraction identifies unwanted resistances and capacitances in the physical layout. These parasitics can affect timing, power, and signal integrity. Extraction tools analyze the layout and generate models for simulation. Accurate parasitic extraction is essential for predicting real-world chip behavior and optimizing performance. Post-layout simulation evaluates the chip's performance after physical design is complete. This step uses extracted parasitics to simulate real-world behavior, checking for timing, power, and functional issues. Post-layout simulation helps designers catch problems that may not appear in earlier stages, ensuring the chip meets all requirements before fabrication. Yield refers to the percentage of chips that function correctly after fabrication. High yield is essential for cost-effective production. Reliability measures how well chips perform over time under various conditions. Designers use robust design techniques and thorough testing to maximize yield and reliability, ensuring products meet customer expectations. VLSI technology is constantly evolving. Emerging trends include 3D integration, FinFET transistors, and advanced packaging techniques. These innovations aim to overcome the limitations of traditional scaling, enabling higher performance and lower power consumption. Staying updated with new technologies is vital for VLSI engineers to remain competitive in the industry. 3D integrated circuits, 3D ICs, stack multiple layers of circuits vertically, increasing density and performance. This approach reduces interconnect lengths and improves speed. 3D ICs present new challenges in design, thermal management, and testing, but offer significant benefits for high-performance applications. They represent a major shift in VLSI technology. A type of transistor used in advanced VLSI chips. Unlike traditional planar transistors, FinFETs have a 3D structure that improves control over current flow. This results in lower leakage, higher speed, and better energy efficiency. FinFET technology is widely used in modern processors and is a key enabler of continued scaling. Advanced packaging techniques such as chiplets and wafer-level packaging are transforming VLSI design. These methods allow multiple chips to be combined in a single package, improving performance and flexibility. Advanced packaging supports heterogeneous integration, enabling the combination of different technologies on one product. This trend is shaping the future of electronic systems. VLSI technology powers the devices we use every day, from smartphones and tablets to smart TVs and wearables. The ability to integrate complex functions onto a single chip has made electronics more affordable, compact, and powerful. VLSI continues to drive innovation in consumer electronics, enabling new features and better user experiences. Modern vehicles rely heavily on VLSI chips for safety, entertainment, and control systems. Applications include engine management, advanced driver assistance systems (ADAS), and infotainment. VLSI enables real-time processing and connectivity, making cars smarter and safer. The automotive industry is a major driver of VLSI innovation, demanding high reliability and performance. Healthcare devices such as medical imaging systems, wearable monitors, and implantable devices benefit greatly from VLSI technology. Miniaturization and low power consumption enable portable and reliable medical equipment. VLSI is helping to improve patient care, diagnostics, and treatment outcomes through smarter, more connected devices. Communication systems, including smartphones, routers, and satellites, depend on VLSI chips for high-speed data processing and connectivity. VLSI enables advanced features like 5G, Wi-Fi, and Bluetooth, supporting the growing demand for fast and reliable communication. The evolution of VLSI is closely tied to advancements in global connectivity. Artificial intelligence applications such as machine learning and neural networks require massive computational power. VLSI chips, including specialized AI accelerators, make real-time AI processing possible in devices from smartphones to data centers. The synergy between VLSI and AI is driving breakthroughs in automation, robotics, and data analysis. Despite its many advantages, VLSI design faces significant challenges. These include managing power consumption, heat dissipation, design complexity, and manufacturing defects. As chips become more advanced, ensuring reliability and yield becomes increasingly difficult. Continuous research and innovation are needed to overcome these obstacles and push the boundaries of what's possible. The future of VLSI design is exciting, with trends like quantum computing, neuromorphic chips, and advanced materials on the horizon. These innovations promise to deliver unprecedented performance and efficiency. Staying ahead in VLSI requires adaptability, continuous learning, and a passion for pushing technological limits. The next generation of VLSI engineers will shape the future of electronics. VLSI design offers diverse career opportunities, from chip design and verification to testing and manufacturing. The demand for skilled VLSI engineers is high in industries like consumer electronics, automotive, healthcare, and telecommunications. A strong foundation in electronics, programming, and problem-solving is essential for success in this dynamic field. Learning VLSI design requires a blend of theoretical knowledge and practical skills. Courses in digital and analog electronics, semiconductor physics, and computer-aided design are essential. Hands-on experience with design tools and real-world projects helps build expertise. Continuous learning is key, as the field evolves rapidly with new technologies and methodologies. VLSI design has transformed the world, enabling the digital revolution and shaping the devices we rely on every day. Its impact spans industries, from consumer electronics to healthcare and beyond. As technology continues to advance, VLSI will remain at the heart of innovation, driving progress and opening new possibilities. Thank you for joining us on this journey through the fascinating world of VLSI design.